Welcome to The Explainer. Today, we're going to dive into a really core concept in digital security, symmetric key cryptography. We're going to look at how we can encrypt massive amounts of information without accidentally giving away our secrets in the process. So, let's start with a really fundamental question. A lot of the data we send has repeating parts, things like file headers or even just big blocks of empty space. The question is, how do we encrypt all that data without the encrypted version shouting to the world, "Hey, look, there are patterns here"? Okay, so the first thing you probably think of is, let's not try to encrypt a gigantic file all in one go, right? Instead, let's break it down into smaller, more manageable pieces.
And this method has a name. It's called a block cipher. It does exactly what it sounds like. It takes our original data, the plain text, chops it into these fixed-size blocks, and then encrypts each one with a secret key. It seems totally simple and effective, but that simplicity is hiding a pretty critical flaw.
So yeah, the process is super straightforward. You chop, you encrypt, you combine. But this very simplicity, this idea of treating every single block in exactly the same way, well, that's where a subtle but really significant weakness is hiding. Let's see what that is.
The whole problem rears its ugly head the second our original data has identical blocks. And trust me, that happens way more often than you'd think. This creates a really dangerous pattern in the encrypted output that an attacker can spot. And here is that flaw plain as day. When block A gets encrypted, it becomes XYZ123. A little later, when the same exact block A shows up again, it encrypts to the exact same thing. The pattern from the original data is perfectly preserved in the ciphertext. Not good. And that's a huge information leak. An attacker might not know what's in block A, but they now know for a fact that it repeated. They've learned something about the structure of your secret data, which is literally the one thing encryption is supposed to prevent. So how do we fix this? The solution is to stop treating each block like its own little island. We need to create a dependency, a link from one block to the next, so that the encryption of any block is affected by what came right before it. We're going to create a chain. This really brilliant technique is called cipher block chaining, or CBC for short. Instead of just encrypting the plaintext block directly, we first mix it with the result of the last encryption. This is what guarantees every single step is unique.
All right, let's walk through how this works. To encrypt the block we're currently on, you first take the ciphertext from the previous block.
Then, you mix that previous ciphertext with the current plaintext block, usually with a really simple and fast operation called XOR. This basically scrambles it all up. And only then do you encrypt that scrambled mess with the secret key. This creates a brand new, unique ciphertext that then becomes the starting point for the next block in the chain. And just look at the effect. It's perfect. Check out block A. The first time it's encrypted, we get XYZ123. But the second time, because it was chained with a completely different previous block, the result is ABC012. They're totally different. The pattern is completely gone. Problem solved. So this chain reaction idea makes our encryption so much more secure. But wait, if every block depends on the one that came before it, doesn't that kind of create a classic chicken and egg problem?
Yep, exactly. Every block needs a previous one to chain with. But the very first block in our message has nothing before it. So where do we start the chain? What do we do?
Now, you might think, well, let's just agree to always start with a block of all zeros. It's a simple solution, but it's a trap. If we encrypt the exact same message 2 different times, we'd get the exact same ciphertext both times. An attacker would see that and know we're sending the same message over and over. We've just moved the repetition problem to a higher level. No, the proper solution is to start with something unique and unpredictable every single time. And this special starting block is called an initialization vector, or IV. You can think of it like a random seed for our entire encryption chain. A secure IV has a few really important properties. It has to be randomly generated for every new message. And here's the kicker. While the IV doesn't have to be secret, in fact, it's often sent in the clear right along with the message, it must be shared with the receiver. They absolutely need that same starting block to unwind the chain and decrypt everything correctly. Okay, so we've solved the repetition problem with this really elegant mix of chaining and initialization vectors. But this very solution brings up one final fundamental challenge. And here it is. For any of this to work, both the sender and the receiver need to have the same secret key and the same initialization vector. So, How do they securely share that information if the only way they can communicate is over the public, insecure internet?
You know, answering that question is one of the biggest challenges in all of cryptography, and it's what leads us away from these purely symmetric systems and into the fascinating world of public key cryptography and hybrid systems, which use some really clever math to solve this exact problem. But that is a topic for another explainer.
I really hope this look into block ciphers and chaining helped demystify a piece of modern security for you. If you found it useful, please hit that like button and subscribe for more explainers that break down complex tech. Thanks for watching.